Machine learning algorithms perceive our world through the rigid rules of linear algebra. To make sense of human information, the system translates everything, a word, a pixel, or a sound wave, into a vector. This acts as a mathematical fingerprint, represented as a structured, ordered list of numbers. An algorithm processes millions of these individual vectors at once, aggregating them into massive computational grids called matrices. These matrices allow computers to store complex human concepts. However, they create a challenge. The algorithm must navigate this grid to determine which data points are actually related. To find related data, an algorithm must mathematically measure the distance between vectors. Take a look at this 2D graph. For a human, the intuitive way to measure the space between 2 points is Euclidean distance, drawing a straight line directly from one to the other. This logic falters when we compare identical concepts of different sizes. Imagine the point near the origin is a short blog post mentioning science 5 times, while the second point, far out on the exact same trajectory, is a textbook mentioning science 500 times. Because Euclidean distance relies on magnitude, the algorithm misinterprets this spatial gap and concludes that the article and the textbook are unrelated. Any metric dependent on size fails when faced with scale. Machine learning requires a measurement immune to magnitude. This updated diagram shifts our perspective. Instead of measuring the gap between the endpoints, we look back to the origin point where both vectors begin. This is cosine similarity. It ignores spatial distance and focuses on the angle between the two vectors. Through vector normalization, the math strips away the length of both lines. The vectors snap to a uniform size, ensuring only their direction remains. The algorithm executes this through the dot product. This linear algebra operation calculates directional alignment without needing to draw the physical shapes. By ignoring how far a line travels and focusing on where it points, cosine similarity resolves the problem of scale. Here is perfect similarity. When vectors point in the same direction, the angle is 0 degrees, yielding a cosine of 1. If vectors point in opposite directions, the angle is 180 degrees, yielding a cosine of -1. When datasets share no relationship at all, they are called orthogonal. Orthogonal vectors are perpendicular, sitting exactly 90 degrees apart. A 90-degree angle results in a cosine of 0, proving the datasets share no commonality. This spectrum from 1 to -1 provides a scale-independent gauge for measuring the relationship between data points. This angular math operates within the massive, multidimensional space of modern machine learning. Take the short article and the massive textbook, for example. They are flagged as a match because their vectors point on the same science trajectory. Search engines use this logic to evaluate vector angles, surfacing hyper-relevant results by matching the direction of your query to the direction of the data. Recommendation systems use this orientation to match user profiles with new content based on their shared alignment. Distance-based metrics like Euclidean geometry often miss these conceptual links because they are distracted by the varying lengths of modern datasets. In the vast matrices of artificial intelligence, the direction of data defines its meaning.